Hi, my name is Baishnavi Prasad and I am a student of Electronics and Communication Engineering at BIT Mesra. This presentation explores the fundamentals of voltage divider biasing, a common technique for setting the operating point of a bipolar junction transistor BJT. We will delve into the key principles, advantages and practical applications of this technique. Some prerequisites for this video are knowledge about working principle of BJT, KVL and KCL, and basic DC biasing networks like fixed bias and emitter stabilized bias. So, why do we need voltage divider biasing? In the previous bias configurations, the bias current IC and the voltage VCE were a function of the current gain beta of the transistor. However, since beta is temperature sensitive, especially for silicon transistors, the actual value of beta is usually not well defined. It would be desirable to develop a bias circuit that is less dependent or in fact independent of the transistor beta. The voltage divider bias configuration is such a network. If analyzed on an exact basis, the sensitivity to changes in beta is quite small. We also have a better chance of choosing a desirable operating point. Now let's move on to the exact analysis of the voltage divider. So first of all, the actual circuit will look something like this one. Uh, to convert this to a network that we can analyze, first of all we will remove all the AC voltages and the capacitors, and we will get this equivalent circuit here. And then R1 and R2 will be replaced by Thevenin resistance, which is RTH. This will be the input resistance, and the we will also introduce VTH or ETH, that will be the input voltage. So now how do we find out RTH and VTH? To find RTH, we will replace VCC by a shorted wire. So we can see that R1 and R2 are in parallel, hence RTH equal to R1 R2 by R1 plus R2. And after we reintroduce VCC, we can see that ETH is nothing but the resistance across the voltage across the resistance R2. So ETH equal to R2 VCC by R1 plus R2. Now let us find the base current IB using the values of ETH and RTH. So after we apply KVL on the input loop, we will get that IB is nothing but ETH minus VBE. Note that VBE is nothing but 0.7 volts for silicon transistors divided by RTH plus beta plus 1 into emitter resistance. This is the IB, and when we apply KVL on the output loop, we will get VCE, which is VCC minus IC times RC plus RA. Now using these equations, let's try to solve this question that we have here. So first of all, we will have to find RTH for this circuit, which will be, as you can see, R2 is 3.9 kilo ohm and R1 is 39 kilo ohm. So we will get 39k into 3.9 divided by 39 plus 3.9 kilo ohms, and this comes out to be about 3.55 kilo ohms. And similarly, ETH will be VCC into R2 by R1 plus R2. If you calculate that, you will get about 2 volts. Now let us redraw the circuit, and you will get ETH here and this is RTH, this is ETH, and here is the transistor. This will be VBE, and this is grounded, and when you apply the equations that we derived in this slide, you will get the value of IB as 0.85 milliampere, and no, IC will be 0.85 milliampere, which is equal to beta times of IB, and VCE will be 12.22 volts. Thank you for watching this video. I hope everything was crystal clear.